Good. And the topic here is really a very technical look at the implementation of CQP queries based on finite state technology. So our starting point are regular expressions in finite state automata. So I suppose everybody's familiar with regular expressions. We use them either in advanced text editors for searching for full text search, or with the command line grep utility for searching strings in files. All computer scientists are very familiar with regular expressions. They know that they are very convenient and also very powerful notation. And they also know that they're highly efficient notation. So taking, for instance, the regular expression shown here, can everybody read that? So it matches strings like CA-BAA or CA-BA-BAA-BAC. The latter one as CA, C, AB, ABA, another AB, and then the A and the final C. Okay, so this regular expression can be converted into finite state automaton shown here, which is fully equivalent and acts as a recognizer for the regular expression. So when it's applied to an input string, say CABAA, it recognizes this regular expression. It recognizes the input, say CABAA. It consumes the input one symbol at a time. So symbols are quite often individual characters in many applications of regular expressions. Starting from the start state Q0, it takes one transition for each symbol consumed. So, for instance, it can take a transition from Q0, the start state, to Q1 by consuming the symbol C, because that's the label on the transition. And then in order to match this particular string, it can take the path to Q3, Q4, Q1, Q5, that's with the last A. And then, because the last C is optional, it can take an epsilon transition without consuming any additional input to reach a final state. So the double circle state here is a final state. At this point, the automaton accepts the regular accepts the input, which means the input matches the regular expression. This finite state automaton is non-deterministic, which means that, for instance, if you're at state Q1 here, and the input is an A, then there are actually three possible transitions you can take. You can take this transition to Q3, you can take this transition to Q2, and you can take this transition to Q5. And actually, after reading the A and transitioning to Q5, you can also transition to Q6 because there's an epsilon transition without any additional input. That's, of course, problematic. That's not how we want computer programs to work. We want a program to be deterministic and take one well-defined transition for each input and each current state. Fortunately, every non-deterministic finite state automaton, here abbreviated as NFSA, can be converted into an equivalent deterministic finite state automaton. The one corresponding to our regular expression is shown down here. So this is the deterministic equivalent of the non-deterministic finite state automaton above. We're not going to go into the details of the construction algorithm. It's actually fairly simple and straightforward algorithm. And as you can see, the resulting automaton isn't much more complex. In other cases, the deterministic automaton might be much larger and more complicated than a non-deterministic one, but it's still extremely efficient when applied to an input because it accepts any input in linear time. For each input symbol, so in this case, if we take the input CABAA again, at each time step, first we consume the C, go to Q1, then we have an A. There's only one possible transition to take at every time point. Now in Q2, when we read a B, again, there's only one transition you can take to Q3, and so on, Q4, and finally back to Q2, actually with the A. And in this deterministic finite state automaton, we actually have multiple accepting or multiple final states, Q2, Q4, and Q5 all accept the input. That's a result from the construction. So in general, finite state automata always have to have a single start state, but they can have multiple final states where they accept the input. So regardless of how complicated this automaton gets, matching a given input sequence, symbol sequence, or given input string is always extremely efficient, because for each symbol that we read, we only have to take a single transition. It's a deterministic algorithm. We can also, while it's common in applications of finite state automata to convert them into deterministic automaton to have this very efficient matching, it's not absolutely essential. So you can also directly work with a non-deterministic automaton. There are two ways of doing that. One is by backtracking, but that can lead to combinatorial explosion in worst case complexity. So there's an example here. If you have a regular expression like this one, there are so many ways of matching the dot asterisk parts, that's arbitrary substrings, for a very long match, that you can have very high complexity, basically cubic complexity in the input length. And it's very difficult to avoid these corner cases. So while backtracking is often used in implementations, it's a rather brittle approach, and users writing inconvenient queries can really break a system with that. The other approach is non-deterministic simulation, which basically applies the finite state automaton as a non-deterministic algorithm. So in this case, again, taking the input A, B, A, A, keep things simple, we start off in this, C, A, B, A, A. We start off in Q0. Then we can read the C and transition to state Q1. We're in state Q1 and have to read in the A. And as I said before, there are actually 4 states we can reach by reading the A: Q3, Q2, Q5, and Q6. So what we do here is, instead of randomly picking one and then backtracking later, we simply activate all the possible target states. So after reading the A, the automaton is in a state where Q3, Q2, Q5, and Q6 are simultaneously active. And then for reading the next input, the B, we have to consider all possible transitions from any of these states. So from Q5 and Q6, we cannot read a B, but we can do so from Q2 to get to Q1, and from Q3 to get to Q4. So after the reading the B, we're in a state where Q1 and Q4 are active, and so on. And as soon, and after reading the last A, or basically after reading the last A, we'll be in a state where I suppose, if I'm not mistaken, Q1, Q2, Q3, Q5, and Q6 are active. And because one of the active states is a final state, the input can be accepted. I spent so much time on non-deterministic simulation because that's exactly how CQP works. And we'll get back to that soon to see why this is necessary. Because regular expressions are known to be convenient and powerful, and because finite state automatas are very efficient recognizers, especially when they're deterministic, but also reasonably efficient with non-deterministic simulation, they seem to be quite a natural choice for formulating query language, especially query languages which we want to match flexible lexicogrammatical patterns. To the best of my knowledge, this was actually invented by CQP in a master thesis by Bruno Maximilian Schulzin, completed in 1994, and then implemented and published by Olivier Christ also in 1994, and then continued in the following years. So the idea here is to use regular expression notation, but instead of taking characters as the basic building blocks, or atoms as we call them, the building blocks are complete tokens, often including also linguistic annotations. And so when you see anything in square brackets in a CQP query, that's a so-called token expression, a Boolean expression that describes, that matches certain tokens. And these token expressions are the building blocks of corpus queries as regular expressions. So we apply regular expression notation to these token expressions. Each of these is treated as an atom, like a single character or match all in a traditional regular expression. In order to avoid the confusion of calling this a regular expression query, I refer to these as finite-state corpus queries, because it's essentially the idea of constructing a corpus query as a finite-state automaton. Most query languages that use finite-state queries also use traditional character-level regular expression for matching attribute tests. So we can use regular expressions, as shown here, to match words that end in the string ABLE, but these are implemented completely separately. So these usually rely on standard libraries such as POSIX functionality or PCRE, the Perl-compatible regular expressions. The ones we're concerned with today are regular expressions over token expressions. So what I'm showing here here you can see three typical examples of token expressions. So this token expression matches any token whose surface form, oh, sorry, that's a mistake. This should, of course, has to be word equals dot plus able. Inside a token expression, I have to specify the attributes. A surface form that ends in ABLE, and that's tagged as a noun with the pen tag NN or NNS. Again, we use regular expression notation here to have a shorthand for the two options NN and NNS. Here's an example of a token expression that matches the lemma attribute, so any form of the lemma light. And the just quoted strings we often see in CQP queries are just a shorthand notation. They're actually token expressions of the form word equals regular expression. And this is the shorthand just a shorthand notation. So you can really think of token expressions as the formal building blocks of a CQP query. And of course, I'm assuming that you know CQP query syntax well enough to know all the different extensions, such as case-insensitive matching and so on. The constraints inside a token expression can be arbitrary Boolean expressions. So you can also use disjunction or connections and negation with an exclamation sign. Okay. In order to evaluate such queries, and so this is not just specific to CQP, there are various other corpus query tools which have adopted similar notation. There's tools like Polycarp, and of course, very famously, the Sketch engine in its various incarnations uses more or less the same query syntax. And as far as I know, at least the original implementation, which is still available as no Sketch engine, also implements these queries as finite-state automata. So let's consider an example query. This is a query that matches an infinitive, a simple form of an infinitive. So it's the word to, case insensitive, surface form to, case insensitive. So we get the upper and lower case versions. Then an optional adverb, and finally a verb in the infinitive in the base form. That's the pen tag VB. So this would match to go, but also to boldly go. This CQP query is translated into the finite state automaton shown here. So we have a start state, and then each transition corresponds to one token expression. Just as in a basic regular or standard regular expression over characters, each transition is labeled with a single character. Here, each transition is labeled with the token expressions. So the positions, the elements of a CQP query don't correspond to the states of the finite state automaton, but to the transitions of the finite state automaton. And so there are different possible ways of constructing this automaton. One possibility is shown here. So the first element, the query always has to start with the surface form 2. So that's our first mandatory transition. And then there's an optional adverb. So if the adverb is not present, I can directly match a base verb, which is performed by this transition from Q1 to Q3, labeled with the token constraint base verb. If the adverb is present, then we take a different branch going through state Q2, which reads first the adverb and then the base verb as the last query element. Everything clear so far? That's not the only way of constructing this. We could have two separate final states. So there's no reason why these have to merge in a single final state. A very common way of creating optional elements would be to just drop this, take the full path, and then allow the finite state automaton to skip an optional element with an epsilon transition. That's what I did with the character level finite state automaton in the previous example. The implementation in CQP works differently and creates the kind of automaton shown here. So there's always a single final state, and it omits any epsilon transitions. Okay, I think it's clear how this is applied. If you have an input string such as to boldly go, at each time step, so I'm going to refer to simulation of a finite state automaton as time steps. In the first time step, we read the word to, matching this transition, go on to state Q1. In the second time step, we would read boldly, which satisfies the constraint part of speech is an adverb. It's an adverb. So we can take this transition to Q2. And in a third time step, we can then, to boldly go, get the verb base form go. So we can take this transition and reach a final state and accept the input as a match of the query. Now I have a question for the audience, and I guess people from my team, such as Philip, should answer this, or Andrew. Is this finite state automaton deterministic? Well, it's a bit of a Schrödinger's automaton. The answer is yes and no. In fact, it's deterministic, because when I'm in state Q1, I can either accept a token tagged VB, or I can accept a token tagged RB, and they are mutually exclusive tags. Of course, I cannot have both on the same token, so I can only ever take one of these transitions, which means the actual path is deterministic. But of course, the CQP query engine or any other query engine has no way of knowing that. In this particular case, if it had some inferencing capability, it might be able to figure out that it's deterministic. But in a general case, it can never know whether two token expressions might match the same or not. There's an example down here. If one of these transitions were labeled lemma equals elephant, and the other were labeled pos equals verb, some form of a verb, then they would probably be mutually exclusive, making the automaton deterministic. But in order to know that, you would actually have to scan the corpus to see whether there are any instances of a lemma elephant that's tagged as a verb, which could either be a tagging mistake or a fairly creative use of the word elephant. So we have to treat such automata as non-deterministic. And that's a key problem of the application of using finite state automata or treating corpus queries as finite state queries, because our automata aren't labeled with individual symbols, as in a formal finite state automaton. They're labeled with complex token expressions, and it's very difficult to see whether two labels are the same, whether they overlap, or whether they're mutually exclusive. So if you try to convert this automaton into deterministic finite state automaton using a general algorithm, you end up with something fairly complicated shown here. because from Q1, you have to consider three possibilities. One is that both of the transitions, actually both token expressions match. So we would transition both to the upper branch and to the lower branch. That's down here. Another possibility is that we have something tagged as RB, but not VB. So one of the token expression matches. And the third possibility is that the first doesn't match, but the second matches. If neither of them matches, of course, then we cannot continue from state Q1. So that's something we don't need a transition for. But here, even we need three transitions with our combinations. Not so bad in this particular case, but if you have a query that has three branches, and here A, B, and C stand for some possibly fairly complicated token expressions, if you want to convert this into deterministic finite state automaton, you actually end up with 7 transitions for every possible combinations of the constraints. So one transition is labeled with A and B and C, all 3 expressions match, one A and B but not C, one A and C but not B, one A but neither B nor C, and so on. So we get this combinatorial explosion, and the resulting finite state automata can become extremely complex, much more complex than you usually get if you apply a determinization algorithm to a standard, to a formal finite state automaton over a finite symbol alphabet. And even worse than that, so it's not just that we get a much larger finite deterministic finite state automaton, selecting the right branch becomes very expensive, because in this case, we actually have to apply 7 complex token expressions for the 7 different branches and then pick the correct one. And even with optimizations, we would still have to evaluate expressions A, B, and C, and then see what combination of truth values obtains and which of the transitions in the deterministic automaton we have to take. In a formal finite state automaton over a symbol alphabet, that's just a simple hash table lookup. So picking the right transition, even if you have dozens of transitions from a state, is very efficient. But for our corpus query, it's no longer efficient because we actually have to test these token expressions, and that's usually a fairly expensive operation. So the only feasible way of implementing finite state corpus queries is to actually use the non-deterministic finite state automaton that we obtained above here, this one, and apply non-deterministic simulation in order to match it against input. With sufficiently low-level implementation written in C or C++ or some other efficient language, this can still be fairly efficient, and we still have effectively linear time complexity in the input. There's a constant which depends on how many transitions we have to test, but still in the end, at each time step, we have a fixed cost. And even if we process a very long input, the processing cost only increases linearly with the input length and not at a quadratic level like we get for context-free grammars. However, despite the efficiency, if we just apply a finite state automaton, such as this one naively, if we apply that naively to a billion-word corpus, that means we would try scanning, or we would try to match the automaton at every possible position in the corpus. So from each of the 1 billion positions in the corpus, we would start in state Q0, see whether we've got a case-insensitive service form 2. And if it's not 2, then we start from the next position. So we're actually we would have to run 1 billion simulations of the finite state automaton. Even though most of these terminate before even taking the first transitions, using the implementation in CWB3 in CQP, it takes roughly 270 seconds to scan a billion-word corpus and produce around 1.5 million matches on my MacBook Pro. So that's not what you want. That's not feasible for some kind of interactive corpus query. So what we need is some kind of indexing, something to narrow down a search space. The obvious solution here is that we have one fairly selective or reasonably selective element, which is the surface form 2 at the start of the query. So if you have an index, an inverted index over the tokens over surface forms, then we can pick out all the occurrences of 2, find the corresponding positions in the corpus, and attempt simulating the finite state automaton only from these start positions. So we basically only try to match when we know there's an occurrence of 2. And that's exactly, again, the approach taken by Corpus Workbench 3. So to actually get it to scan through the entire billion-word corpus, I had to use a certain dirty trick. If you just run the query above in CQP, what it does, it finds all the forms of 2, case insensitively, so upper and lowercase spellings. It identifies roughly 23 million occurrences of 2 in the entire billion-word corpus, and then it will just run 23 million simulations instead of a billion simulations of the finite state automaton. This brings down execution time to 35 seconds. That's still a bit painful, but it's much better than 270 seconds. And you can see what a big factor improvement you get from these lookup optimizations. And that's for a query that returns 1.5 million matches. So even just generating these matches is going to take some time. If the first element of the query were more selective, some more specific words such as elephant, then of course the search space would be narrowed down a lot more, and the query would be executed in less than a second, even on a billion-word corpus. Okay. I have one final example in this general section, which sort of serves a bit as a running example when I discuss the specific implementation of finite state queries in the Corpus Workbench. So that's the query Simon says. I assume you can all read the query and know what it matches. So the query consists of a large group, of a disjunction between 2 alternative branches, followed by the verb to say. So lemma say, and we check that it's part of speech tag as a verb. And what we match beforehand is basically a noun phrase. So there are 3 alternatives here. The first alternative in the first line, that's an optional determiner, any number of adjectives followed by a singular or plural noun. So that's determiner phrase, or a very simple form of determiner phrase with a bit of flexibility. The second option are 1 or more proper nouns, so that would match a proper name. And the third option is a single pronoun, so that basically matches the third form that a noun phrase can typically take. So what I've written down here with this already fairly complex query is a simple pattern for a general noun phrase followed by the verb say. Okay, exercise for the audience. Translate this into a finite state automaton. You've got 30 seconds. Since we're already quite late, I won't wait for you to construct the automaton. Here's the automaton that you get, or at least the automaton that CQP generates for this query. So all the automata I show here are the actual ones used by CQP when executing the specified queries. If you read this, if you match the transitions here against the alternatives, you can figure out what's happening. So let's start with the third alternative, where the noun phrase is just a single pronoun. That's given by a transition to state Q2. And then, of course, after the alternatives, we have to read the verb to say, using this transition to get to the single final state. So basically, this path corresponds to the third alternative, followed by the final token expression. The path at the bottom corresponds to the second alternative. That's again regular expression notation, clean plus. So we have 1 or more of these token expressions. The first transition from start state matches a single proper noun, reaches state Q3, and state Q3 has a loop which can read additional proper nouns, any number of additional nouns, proper nouns, and stay in state Q3. So that's how you implement a clean plus. One way of implementing clean plus, and a way that's chosen by CQP. You have one transition that's mandatory, and then you can read any number of additional proper nouns. And then the query is completed by matching a form of the verb to say to reach the final state. So the only bit that's still missing is the first branch of the alternative group, the full determiner phrase, and that's this upper part of the finite state automaton. So let's first assume that the determiner here is were not optional. Then we have to start with a transition for a determiner as shown here. We have any number of adjectives. Because this is a clean star, the adjectives are actually optional. So optional adjectives are matched by a loop on state Q1, where we can read any number of adjectives, but we don't have to take the loop, so it's actually optional. And the noun determiner phrase is completed by matching a single common noun, NN or NNS. Since the initial determiner is actually optional, we have to be able to skip this transition. As I said before, this could simply be achieved by adding a parallel epsilon transition. But because CQP doesn't like epsilon transitions, what it does instead is to allow to add transitions for the possible continuations. So if I skip the determiner, then the first element to be read could also be an adjective. So I add this transition. If the first element is an adjective, I can directly get to state Q1 and then read additional adjectives. But since they're also optional, I can also directly read a noun, and that's given by this transition, jump directly to state Q2 and just match the final token expression. Okay, I admit that was probably quite a lot, but that's the most complicated finite state automaton we need. And as I said, you can just download the PDF and look at that at leisure and see if you can reconstruct. If you cannot reconstruct it from the query, I've probably made a stupid mistake. Just get in touch with me and let's get that fixed. This, by the way, actually highlights a problem of the general strategy used by CQP to match queries, which is to look up only the initial transition, first transition from the start state in the index. Because here, what's actually highly selective, the only selective element of this query is the last token expression, the verb to say. So if I looked up the last expression in the index and then sort of tried matching from right to left, so simulating the automaton backwards, that would be very efficient. But looking up the first positions, the first transitions, which basically finds all determiners, all adjectives, all nouns, all pronouns, and all proper nouns, is extremely inefficient. And this is actually one of the worst queries you can possibly write in CQP. I have some numbers on that further below. And with that, we can get to how things actually work in CQP. You've already got the rough idea. I want to add some detail on that now. You don't have to take my word for it. You can actually ask CQP to display the finite state automaton and even allow you and even enable you to trace the simulation of the finite state automaton. Here's the magic incantation. So these two debug options tell CQP to display the finite state automaton generated for every query that you enter. The additional symbols here should only be used if you know you have for carefully constructed query on a small corpus, because that will give you a full trace of the simulation of the finite state automaton for every possible start position. So if you want to understand how things go wrong or what happens in a simulation, add these options. If you just want to see the finite state automata, just use the first two options. The recommended corpus is the small corpus included as sample data in a CWB encoding tutorial, the very short stories, or VSS corpus. So here I'm directly activating this corpus. All the examples in this document were designed on the VSS corpus and can be tested there. Okay, so here's the kind of output you get for our first query. So remember, that's the infinitive query to add optional adverb and base form of a verb. That's sort of an intermediate representation here, which shows you the elements of the query, and that just appear in their numbering order. And unfortunately, they're just separated by these dots here, which means concatenation of elements in the query. So this can be a bit difficult to read, but the idea is try to figure out what the individual token constraints are. So here the first token expression, that's actually token expression 0. Word equals some regular expression 2. Regular expression because it's matched case insensitively. This is the second token expression, part of speech equals adverb. That's token expression 1. And this is the last token expression, part of speech equals verb. That's token expression 2. So this numbering is implicit in the display here. So the 0, 1 here, forget about that. That's just additional information about repetition operators. Here the question mark and alternatives. So basically you get the mixture of the regular expression notation and the token expression. We just need this output, the eval tree, to enumerate the token expressions. The query is then converted into a search string consisting of some regular expression-like notation, where the brackets here, for instance, indicate optionality, over the token expressions labeled 0, 1, and 2. So these 0, 1, and 2 actually refer to the 3 token expression we've enumerated here. This is passed to a standard regular expression compiler library, which creates a finite state automaton that's shown as a transition table at the bottom. So now we can actually write down the finite state automaton. The start state is always state 0. And then we have transition to state 1, labeled with the token expression 0. From state 1, we have 2 possible transitions. We can go to state 2, labeled with the token expression 1, or we can go to state 3, labeled with token expression 2, and we can go from state 2 to state 3, labeled with token expression 2. And finally, S3 is the final state. There will always be only a final state, and there are usually no additional transitions from the final state. So 3 here marks the finite state. And that's exactly the automaton I've shown you above. So with this output, you can actually turn every CQP query into a finite state automaton and see whether it matches the ones in the paper here. So how does the simulation work? Basically, non-deterministic simulation, as I've shown above. Just that instead of taking transitions based on an input symbol and taking multiple transitions to multiple state only if you have the same symbol on all transitions, all the token expressions on all the possible transitions from the current state are tested against the current input token, and then all matching transitions have to be taken. So it's really exactly the same procedure. Let me repeat that non-deterministic simulation is actually based on 2 central assumptions which hold for finite state automata. One that's very well known is that finite state automata don't have memory. That's why we can just keep track of active states. If there are multiple paths that lead us to the same state at the same time step, they basically reach the same state by consuming the same input. And it doesn't matter which path the FSA has actually taken. From a given state at a given time step, I can always continue in the same way. So we can forget about multiple paths leading us to the same state. We just have to record that the FSA has somehow reached this state. That's what I call the no memory assumption. So it's usually said that finite state automata don't have a memory. They don't store anything except in the information in being in a certain state. Another assumption that's less explicit is that the non-deterministic simulation is time synchronized, which basically means that at every time step, we consume exactly one symbol from the input, or in our query case, one token from the input. And that means the reason why this is important is that if two paths reach the same state at the same time step, where basically they are merged into this active state, they correspond to the same input. If they correspond to different parts of the input because they're out of sync, then of course, by merging them, we might lose one path through the automaton, and that again might lose a possible match. And so basically what we do is we carry out the simulation as I've shown before, until, and that's here, shown here, either we reach a final state. So the final state is one of the active states. Then we can accept the input that has been processed as a match. Or there are no more active states. Then we can't find, and we haven't found a match at this position in the corpus. And actually CQP always also imposes a hard limit on the maximal length of a match. There's an option to set this hard limit, which is to avoid some basically a query that could match the entire corpus as a single match. So at some point, if you write a query that can generate very long matches, at some point CQP is going to stop it. Okay. In order to make queries efficient, as I said before, we use an inverted index. So C Corpus Workbench 3 builds an inverted index for every positional attribute. There's no corresponding index data structure for structural attributes, which is also why structural attributes are much less efficient in matching than positional attributes. The index is only for a single attribute, so there are no combo indexes for combining multiple attributes, and there are also no n-gram indexes, which restricts the way in which this index can be used to restrict the search space. There's a description of the matching procedure for the two queries above. Let's just take a quick look at this and I'll try to illustrate it. So I've already briefly sketched what happens for this query. So first, we make a list of all the occurrences of 2 in the corpus in any case form, in a lowercase or uppercase form. And then for each of these possible starting positions, we carry out non-deterministic simulation until either a final state is reached, then we accept a match at this position, or until there are no longer any active states without reaching a final state, and then the FSA doesn't match at this position. If we reach a match, we record the start and end point of the match. If we don't find a match for a given start position, this item from our initial match list is deleted, and at the end, we only retain the items that led to a complete match. So that's exactly how the implementation works. This is very easy in this case because we only have a single transition from the start state. But for my favorite query here, the Simon-Says query, we actually have 5 different transitions from the start state, which I've enumerated here. So we actually have to carry out 5 different index lookups depending on which transition we want to take from the start state. And the query is executed in 5 separate passes. So if you set the progress information, display progress information in CQP, you might see pass 1 of 3, pass 2 of 3, and so on. You've got 1 pass for each possible transition from the start state. So in the first pass, we make a list of all the occurrences of determiners in the corpus. And then for each occurrence of a determiner, we try to simulate the finite state automaton. Because we know we want to take this transition, this is actually hard-coded then. So in this pass, the automaton will only take the first transition as an initial transition. It'll ignore 2, 3, 4, and 5. And it won't test the token constraint here again because we already know that it matches at this position. So that's a small optimization. Then in a second pass, we do the same for the second transition. We find all the adjectives and then only go through the second transition when we try a match, and so on for the other 5. So that means after these 5 passes, we actually get 5 lists of matches, 1 for each possible first transition we can have taken. So what you see here is a text description of this algorithm. And then at the end, after the passes, the 5 lists have to be merged and any duplicates in these are discarded. So that's exactly how the implementation works. And here are the numbers I promised. If you apply the Simon-Says query, that's about, as I said, it's about the worst query you can formulate, to billion-word corpus, it takes 10.5 minutes on my MacBook Pro. And it's not Apple's fault, it's really just that inefficient. If you've ever talked to me about optimization, I might have hinted or explained why CQP cannot optimize this in the way that, for instance, Paul Meurer did in his Corpuscle framework, which is a different query engine that tries to optimize regular expressions in a better way by using index lookups for arbitrary transitions in the finite-state automaton. There are reasons why CQP can't do this. So what I usually recommend is to, if you know that there's a highly selective element and know what it is, then you can do pre-filtering. For the Simon-Says query, the selective element is the verb to say. So if we assume the match is actually contained in a single sentence, which at least was our intention with this query, of course, then we can only find a match in a sentence that contains the verb to say. So what we do here is actually a 3-step procedure. 1, we find all the sentences containing say, expand to S to get the complete sentences and discard duplicates. 2, we activate the query result, this list of sentences, as a subcorpus, and then carry out a subquery only within the sentences that contain the verb say. And then we run the ugly Simon-Says query. It's still ugly because CQP has to start by looking up all the determinants and all the nouns and all the adjectives in inverted index, but then it automatically filters them against the list of sentences containing the verb say, and carries out the simulation only for these sentences. And that brings down execution times at least to less than 100 seconds. So around 1.5 minutes instead of 10.5 minutes. So again, a worthwhile optimization, even though it's still much slower than I'd like it to be. Okay, so one of the hard things to explain about CQP is that there are different matching strategies. Most people probably weren't even aware of these, except for advanced users who got through most of the CQP query tutorial. However, matching strategies has recently been enabled in CQP Web. So now that you can actually change the matching strategy within CQP Web, I think it's probably becoming much more widely used. There are actually 4 different matching strategies. Standard is the default strategy, which most people will be using. I often describe this as early matching, which means stop matching. It's sort of a non-greedy matching strategy where you stop as soon as you found a match and don't try to find a long match. There's a longest match strategy. That's the other one that can be of interest, to find the longest possible match. So that's a more greedy matching strategy. For completeness, I also implemented shortest match, although that's rarely of interest. And finally, there's something euphemistically called traditional, which is the strategy used by the original implementation of CQP before version 3.0, and which, as you're going to see in a moment, does something quite horrible about matching, though it does have its uses too. So as an example, consider this rather boring query, which matches a simple noun phrase, simple noun phrases. So again, we have an optional article at the start, any number of adjectives, and finally, 1 or more common nouns. So here, I allow multiple common nouns so that we can also include noun compounds in the noun phrase. So if the head of the noun phrase is a compound like train station or computer program, it actually consists of multiple tokens tagged as nouns. So our typical query, which omits the plus modifier, here the plus quantifier, wouldn't match the entire, would just match train or just match computer. So that's how you want to match noun phrases. Actually, if you run this query, you'll find that it doesn't match the compound nouns, because in a standard matching strategy, the query stops as soon as it has found a match, and because additional nouns, noun tokens are optional here, the first noun in the noun phrase actually is sufficient to obtain a match. Here's the finite state automaton corresponding to this query. Again, that's a nice little exercise to try on your own. If you want to get into this, it should be fairly straightforward based on the query above. It's similar to the Simon Says query, to a fragment of the Simon Says query. So that's how this works. Actually, I didn't check this against CQP, whether it actually has the loop on the final state or matches this in a different way. Now we're going to apply this query using CQP to find the noun phrase, the cozy little coffee shop. Recall what CQP does is to execute the query in 3 passes in this case. A first pass for the transition where we start with an article, a second pass for this initial transition where we start with an adjective, and a third pass for this transition where we start with a noun. The actual simulation in each of these passes is the same for all matching strategies except longest. So up here is what happens if you set matching strategy to standard, shortest, or traditional. Down here is what happens if you set it to longest. So in the first pass, we start from the article, the, and then simulate the automaton, the, read cozy and little with this loop on the, let me highlight that. So we start with the determiner. Then we use the loop twice to read cozy and little. And then this transition to read coffee. And because now we've reached the final state and we use this early matching strategy, we stop the simulation here and accept the cozy little coffee as a match of the query. So that's the match we get in the first pass. Now in the second pass, we find all the instances of adjectives. There are actually 2 adjectives in this noun phrase. So we have cozy as a potential starting point and little as a potential starting point. The simulation is run from both starting points. So CQP doesn't figure out that it's actually a nested, that sort of the second one is just a part of the first query match. So it runs 2 separate simulations and it will find both matches in the second pass. And in the third pass, we find all the nouns, coffee and shop. So we actually find this match in the third pass, and we'll find another match, which I forgot to mention. Just shop will also match in the third pass. So that will produce another match of the query that I omitted here. What happens in the standard, and this is the same for all 3 matching strategies. So we get these 3 lists of matches. We get these 4 matches in total plus shop as a 5th match. The difference between the strategy actually happens in the merging phase. In a standard matching strategy, if I have multiple matches, so as you can see here, I have 4 matches that share the same endpoint coffee and which are nested. And in a standard strategy, all the shorter ones are discarded and only the longest ones are kept, which has the effect of including optional elements at the start of the query, but excluding them at the end of the query because of the early matching strategy. And now you can guess what happens in the other strategies. With the shortest matching strategy, I keep the shortest of the overlapping matches. And in this case, it's not just if they have the same endpoint. whenever I have nested matches, only the shortest of these will be kept. As I said, that's rarely particularly useful. The traditional strategy does something weird, or rather it doesn't do anything at all. It just keeps all of the matches. So if you run CQP in traditional matching strategy mode, you'll actually get 4 matches for the cozy little coffee, the cozy little coffee, cozy little coffee, and coffee. Finding a use case for this behavior is left as an exercise to the reader. Okay, and finally, if you have longest matching strategy, the difference is that now, once we've reached coffee and state Q2, we can accept the input, that's a potential accept, but since we still have an active state, we try to continue the simulation, take the loop here to reach shop, and then accept the match when we can't continue any further. So setting matching strategy to longest has the effect of including optional elements at the end of the query. Apart from that, it behaves in the same way. So the first path gives us 1A, the second path gives us 2A and 3A, and the third pass gives us 4A. And then in a final merging step, whenever we have nested matches, only the longest one is kept. So in this case, it will again select the cozy little coffee shop. Okay, and after this explanation, you should finally be able to figure out exactly what to expect from CQP in the different matching strategies. Last thing for today, because I don't want to end on a positive note, there are a few very big dragons buried in all of this. Basically, it's just a single problem. The non-deterministic simulation of finite state queries relies on the fact that they're finite state, which means that they're time synchronized and that the automaton doesn't have memory. Unfortunately, that isn't true for CQP. So actually, both assumptions are violated by certain CQP queries. And since the CQP queries aren't truly finite state, simulation of the finite state automaton can go horribly wrong in some cases. And that's not, I wouldn't see this, please don't see that as a bug in CQP. It's a fundamental problem of this implementation of finite state corpus queries. And it's very difficult to work around that and still have an efficient implementation. So briefly, there are 2 reasons why you would get violations of these assumptions. The first issue are zero-width elements. I suppose the most common zero-width element that many people will use in their queries are XML tags that match the start and end point of S-attribute regions. So whenever you match the beginning of a sentence or match a noun phrase, as in this case, with the start and an end tag, you actually include zero-width elements. It means elements of a query that don't consume a token. This query, so that actually, you haven't had time to read the query, it starts with the surface form with, and then we have 2 options, either a pronoun or a noun phrase that consists of a single token. I hope you're all familiar enough to recognize the match all for an arbitrary token. This is translated into very straightforward finite state automaton as shown here. So for the alternatives, we get 2 branches, one that has just a single transition. And the first branch, the upper branch, has 3 transitions because each element of a CQP query, even the zero-width elements, the XML tags, is translated into single transition. So the finite state automaton constructed by CQP actually processes a single query element at each transition, either a token expression or an XML tag or some other element. So the problem is if you apply this to the input, say, with them, at time step 1, let's say that's our position 42 and 43. So we start here in position 42. At time step 1, we read the with, advance to position 43. or basically we're before position 42, and after reading with, we're before position 43. At this point, and actually that will be wrapped in a noun phrase. Them, every pronoun is identified as a noun phrase in the VSS corpus, so that'll be wrapped in the corresponding XML tags. So at this point, we actually have non-determinism. We can either match the next token at position 43, which is a pronoun them. So we have to take this transition at time step 2, and then advance the position to 44 after them. So we're prepared to match the next token. But we can also, so that's time step 0, time step 1, time step 2. But we can also take the transition which reads the 0 with XML tag, or label with the 0 with XML tag, which matches at this place, and reach state Q2 at time step 2. But we're still at corpus position 43 because that was 0 width. And then at time step T3, we consume the them with the match all to get to 44, and then match the end tag to reach state Q3 at the same corpus position, but 2 time steps later than the other branch. So that is actually isn't a problem. This query is going to work perfectly fine. The problem is that the simulation has gotten out of sync. We reach the same state by consuming the same input, namely with them, at different time steps. And that's something that the non-deterministic simulation doesn't allow, and that can lead to problems in the right context. If you want to construct a problem here, those of you who know enough CQP could put a target marker on the pronoun in the noun phrase, but forget it in the other branch. And then you're surprised that you never get the target marker, because the second branch actually reaches the final state earlier, and thus this match is accepted, while the longer upper branch is still being processed and never reaches the destination. So you can see this already can create a problem. There are other zero width elements, zero width assertions, which are mainly used by very advanced users, so by CQP experts. So many of you might not even be aware of zero width assertions. This is the point where Philip and Natalie should start weeping, because they might recognize this use of zero width assertions sort of as placeholders for putting target markers, which creates exactly the same problem. This introduces a one-time step delay because we have a transition labeled with a zero width element. Okay, so that's problem 1. The time sink assumption doesn't hold. Unfortunately, it's also not true that finite state automata for finite state queries don't have memory, because advanced users can set labels on token expressions and later refer to the corpus positions recorded by that label. So that's a query that finds an expression like eye to eye or no face to face. It's translated into a very straightforward finite state automaton, or what looks like a finite state automaton, but one that has memory, because in the first transition, in addition to checking the token expression, we actually set a label to remember this position in the corpus, and that this label is carried through the other states until it's read out in a final transition to test the lemma constraint here. It's more or less exactly like back references in POSIX regular expressions. You know, this \1 and so on, which you can use to pick up a previous element, which leads to similar problems. At least if you have a Mac and try to use grep with UTF-8 input, it turns out that the back references are completely botched. The implementation of back references is completely botched, and it produces utter nonsense. CQP has similar problems. So you could think of it as the Mac of corpus query processes. Even if you don't use label references explicitly, if you're not aware that you're using, you might be using them without being aware of the fact, because they're used internally. Whenever you set a target marker, such as here, that's actually stored as a label reference internally to keep track of the target position until we've reached the final state and can record it into our result set. And whenever you use balanced open and close tags, then CQP will make sure that they match a single region of an S attribute, not just an arbitrary start of a region and an end of a region, but it's the same region. And in order to keep track of that, CQP stores a kind of a label reference when taking this transition, which identifies the region here. And when it's reached the end of the region, it checks that that it's the end of the region corresponding to the start tag. So we're actually using label references all the time implicitly without being aware of that. Okay, and that brings me to the end of my talk. That's where the real exercise for the reader starts. Knowing about these two problems, if you use the right combination of zero-width elements and memory label references, then you can construct queries that aren't evaluated correctly because of what I call state obliteration. That two paths lead to the same state at the same time step, but either they're out of sync in time or they contain different label references. And when merging the paths, one of them wins. So basically we lose information from all the other paths. And if they're not in sync or if they have different label references, then the resulting match can be affected. Here is one example of a query. This query finds matches in the VSS corpus. This finds a single match, namely dine in a cozy little restaurant, which I think is a nice finish to this talk, even though we can't do that now. So it starts with the surface form dine, and then it does something a bit weird. It has a disjunction that either matches this sequence, a start of a prepositional phrase, a single arbitrary token, then the start of a noun phrase, or it matches the sequence preposition, article, adjective, and then this disjunction is followed by an adjective and a noun. So let's just see how this matches the noun phrase, the example above. Forget all the target markers; they are just introduced so that it's easier to track when you use the debug simulation and SimTab debug. The target markers help you track exactly what's going on in the query and what information the states record. So if we try the first branch here, dine matches the first word, then this element matches the start of a prepositional phrase. This element matches the in. This element matches the start of the noun phrase. So if we've taken the first branch, then we'd expect an adjective and a noun, but actually we get a determiner here, so this attempt at matching fails. But if we take the second branch, so the second branch expects a preposition, here in, an article, a, an adjective, cozy, and then another adjective, little, and the noun restaurant. So by taking the second branch, we can match, which means this query should match dine in a cozy little restaurant in VSS, and it actually does. Now, the miracle is if you rewrite that query as shown below, as dine 2, if you look at this carefully, the only thing I've done is that I've swapped the first and the second alternative in the disjunction. It's exactly the same query, just different ordering. It will find 0 matches in the VSS corpus. Okay, thanks for your attention. That's the exercise for you. Perhaps you can tell me, you can make a guess of why that happens. Or if you're really curious, either read the explanation in the PDF or ask me in the discussion. Thanks. I think we should have asked you to sign a non-disclosure agreement before I tell you that there's a bug, that there are bugs in CQP.
I would comment that a lot of what we've just seen in that talk explains both A, why Stefan decided that he and I should rewrite most of Corpus Workbench from scratch in version 4, but also B, why we are certifiably insane for deciding that it was a good idea to do.
But at least now we have a sketch of how to do it or how not to do it.